Matrix chain multiplication is an optimization problem that can be solved using dynamic programming. Given a sequence of matrices, the goal is to find the most efficient way to multiply these matrices. The problem is not actually to perform the multiplications, but merely to decide the sequence of the matrix multiplications involved. We have many options because matrix multiplication is associative. In other words, no matter how we parenthesize the product, the result obtained will remain the same. For example, if we had 4 matrices A, B, C, and D, we would have C, D equals D equals A, D equals A. However, the order in which we parenthesize the product affects the number of simple arithmetic operations needed to compute the product, or the efficiency. For example, suppose A is a 10 times 30 matrix, B is a 30 times 5 matrix, and C is a 5 times 60 matrix. Then, C equals 1500 plus 3000 equals 4500 operations. A equals 9000 plus 18000 equals 27000 operations. Clearly the first method is more efficient. With this information, the problem statement can be refined. How do we determine the optimal parenthesization of a product of n matrices? We could go through each possible parenthesization, requiring a runtime that is exponential in the number of matrices, which is very slow and impractical for large n. A quicker solution to this problem can be achieved by breaking up the problem into a set of related subproblems. By solving subproblems one time and reusing these solutions, we can drastically reduce the runtime required. This concept is known as dynamic programming, a dynamic programming algorithm. To begin, let us assume that all we really want to know is the minimum cost, or minimum number of arithmetic operations, needed to multiply out the matrices. If we are only multiplying 2 matrices, there is only one way to multiply them, so the minimum cost is the cost of doing this. In general, we can find the minimum cost using the following recursive algorithm. Take the sequence of matrices and separate it into 2 subsequences. Find the minimum cost of multiplying out each subsequence. Add these costs together, and add in the cost of multiplying the 2 result matrices. Do this for each possible position at which the sequence of matrices can be split, and take the minimum over all of them. For example, if we have 4 matrices A, B, C, D, we compute the cost required to find each of, and making recursive calls to find the minimum cost to compute A, B, C, AB, C, D, and B, C, D. We then choose the best one. Better still, this yields not only the minimum cost but also demonstrates the best way of doing the multiplication. Group it the way that yields the lowest total cost, and do the same for each factor. However, if we implement this algorithm, we discover that it is just as slow as the naive way of trying all permutations. What went wrong? The answer is that we're doing a lot of redundant work. For example, above we made a recursive call to find the best cost for computing both ABC and AB. But finding the best cost for computing ABC also requires finding the best cost for AB. As the recursion grows deeper, more and more of this type of unnecessary repetition occurs. One simple solution is called memoization. Each time we compute the minimum cost needed to multiply out a specific subsequence, we save it. If we are ever asked to compute it again, we simply give the saved answer, and do not recompute it. Since there are about n2/2 different subsequences, where n is the number of matrices, the space required to do this is reasonable. It can be shown that this simple trick brings the runtime down to O from O, which is more than efficient enough for real applications. This is top-down dynamic programming. From pseudocode. Matrix I has dimension p, I1, x p, I, for I equals 1, n matrix chain order, length, p, equals n plus 1, n equals p, length 1, m, I, j, equals minimum number of scalar, multiplications needed to compute the matrix I plus 1, Aj equals Aij. Cost is 0 when multiplying one matrix for M. I equals 0. 4. L is chain length for J equals I plus L minus 1, M, I, J equals MAXINT. 4. Q equals cost, scalar multiplications Q equals M, I, K, plus M, K plus 1, J, plus P, I 1, asterisk P, K, asterisk P, J, if M, I, J equals Q, S, I, J equals K, S, I, J equals second auxiliary table that stores K, K equals index that achieved optimal cost. Note: the first index for P is 0 and the first index for M and S is 1. Another solution is to anticipate which costs we will need and pre-compute them. It works like this. For each K from 2 to N, the number of matrices, compute the minimum costs of each subsequence of length K, using the costs already computed. The code in Java using zero-based array indexes along with a convenience method for printing the solved order of operations. Public class matrix order optimization, protected int M, protected int S, public void matrix chain order, int n equals P, length 1, M equals new, int n S equals new int n 4, int J equals I plus E, M, I, J equals integer, max underscore value, 4, int Q equals M, I, K, plus M, K plus 1, J, plus P, I, asterisk P, K plus 1, asterisk P, J plus 1, if M, I, J equals Q, S, I, J equals K, public void print optimal parenthesizations, void print optimal parenthesizations, if print optimal parenthesizations, print optimal parenthesizations, string istr equals inner result, I, underscore result, string jstr equals inner result, j, underscore result. System.out.println, inner result, I equals true, inner result, j equals true. At the end of this program, we have the minimum cost for the full sequence. Although this algorithm requires O time, this approach has practical advantages that it requires no recursion, no testing if a value has already been computed, and we can save space by throwing away some of the sub-results that are no longer required. This is bottom-up dynamic programming, a second way by which this problem can be solved. More efficient algorithms. There are algorithms that are more efficient than the O dynamic programming algorithm, though they are more complex. Hu and Xing, an algorithm published in 1981 by Hu and Xing, achieves O complexity. They showed how the matrix chain multiplication problem can be transformed into the problem of triangulation of a regular polygon. The polygon is oriented such that there is a horizontal bottom side, called the base, which represents the final result. The other n sides of the polygon, in the clockwise direction, represent the matrices. The vertices on each end of a side are the dimensions of the matrix represented by that side. With n matrices in the multiplication chain, there are n-1 binary operations and cn-1 ways of placing parentheses, where cn-1 is the th Catalan number. The algorithm exploits that there are also cn-1 possible triangulations of a polygon with n+1 sides. This image illustrates possible triangulations of a regular hexagon. These correspond to the different ways that parentheses can be placed to order the multiplications for a product of 5 matrices. For the example below, there are 4 sides, A, B, C, and the final result ABC. A is a 10 times 30 matrix, B is a 30 times 5 matrix, C is a 5 times 60 matrix, and the final result is a 10 times 60 matrix. The regular polygon for this example is a fourgon, i.e., a square. The matrix product AB is a 10 by 5 matrix and BC is a 30 by 60 matrix. The two possible triangulations in this example are polygon representation of C, polygon representation of A. The cost of a single triangle in terms of the number of multiplications needed is the product of its vertices. The total cost of a particular triangulation of the polygon is the sum of the costs of all its triangles. C plus equals 1500 plus 3000 equals 4500 multiplications. A plus equals 9000 plus 18,000 equals 27,000 multiplications. Huanxing developed an algorithm that finds an optimum solution for the minimum cost partition problem in O time. Generalizations. The matrix chain multiplication problem generalizes to solving a more abstract problem. Given a linear sequence of objects, an associative binary operation on those objects, and a way to compute the cost of performing that operation on any two given objects. Compute the minimum cost way to group the objects to apply the operation over the sequence. One somewhat contrived special case of this is string concatenation of a list of strings. In C, for example, the cost of concatenating two strings of length m and n using stricat is O. Since we need O time to find the end of the first string and O time to copy the second string onto the end of it, using this cost function, we can write a dynamic programming algorithm to find the fastest way to concatenate a sequence of strings. However, this optimization is rather useless because we can straightforwardly concatenate the strings in time proportional to the sum of their lengths. A similar problem exists for singly linked lists. Another generalization is to solve the problem when parallel processes are available. In this case, instead of adding the cost of computing each factor of a matrix product, we take the maximum because we can do them simultaneously. This can drastically affect both the minimum cost and the final optimal grouping. More balanced groupings that keep all the processes busy are favored. There are even more sophisticated approaches.